Hello, welcome back. In this segment, I will quickly define what is a field. Field is an important mathematical structure we need in cryptography, so I will formally define it. So we have a field F, which we'll define it as follows. It would require two operations, plus and multiplication. Okay. F itself is a set. Plus is addition. Multiplication is denoted by cross. You can have a special meaning for plus and special meaning for multiplication depending on the set you are working with. But let's assume plus means additive, multiplication is shown as the cross symbol. Okay, so F itself is a set of elements. It can be finite or it can be infinite. So we will later define a finite field more specifically, but for now, what is a field? A set F is a field if F with just plus, right, is a group. So we already defined what a group is earlier, so I have to ask you to watch the group videos. So this must be a group already. Okay. And of course, a group means you need to also have an identity element. The identity element is 0 as the identity element, right? Identity element is 0. All right. What about the multiplication? For the multiplication, we need to remove 0 from the set F. I'm removing 0 from the set F. And this must form a multiplicative group. This is additive group. This is multiplicative group. Okay, so that's the second property. But the third property, if you take any three elements A, B, C from the field, from the set F, you can do A times B plus C as A times B plus, I can show you a multiplication here because later we will define more precisely what is the meaning of multiplication and addition. But for now, it's okay to assume the regular multiplication, regular addition that we are used to in our basic math. Okay, so this is the distributive property. First property is that F must form an additive group with the 0 as identity element. F without 0 must form a multiplicative group with 1 as the identity. Okay, that means there are two identities, 0 as identity, 1 as identity for two different groups, of course. The third property is the distributive property. Okay, A times B plus C is same as A times B plus A times C. If all these three conditions are true, then we say the given set F is a field. That's the definition of a field. F is a set of all elements. It can be finite or it can be infinite. Okay. And what is one classical example often we give is if we assume F is the set of all real numbers. Okay. The real line that we are used to. You take 0 here, and this is the increasing direction, and this is the decreasing direction, right? If you do any addition, the result is also a real number. So it's clearly, if you replace F by R, you have 0 as identity element, and all the basic properties of group holds true in the context of the F being the set R. Okay, and that same thing, you get rid of 0, every other element has a multiplicative inverse in real line. You know, if you take number 2, the multiplicative inverse is half. Okay. So half is somewhere here. Okay, so multiplicative inverse exists, and one is identity element. So we already proved that this is also a group. Okay, the third property is coming straight from the definition of how addition and multiplication works in real numbers. So this is also true. So this is one classical example of a field. Okay, this is an infinite field because, as I said here, the numbers are going on both side directions. Therefore, this is an infinite set. Okay. In cryptography, for example, in GCM mode, which we will talk later, or in AES algorithm, finite fields are going to be used. So the set F will be finite, okay, which I will talk about later, how to construct a finite field. Only a finite number of elements, of course. That kind of set is called a Galois field, okay. We will talk later about Galois field, but this is just quickly give you a definition of what is a field, okay, and an example. This is an example.